We might not notice, but tremendous technology and mind-boggling science constantly surround us in the products we use every day. Behind their practical use lurk hidden histories, dramatic discoveries, and awesome experiments. They are wicked inventions. Coming up, snowmobiles. What is the connection between a tunnel and its manufacturing process? Air conditioning. We find out how the quest to rid the world of soggy magazines led to a rather cool discovery. The immersion suit. The important piece of protective clothing that just might save your life at sea. We reveal its fascinating production process. We reveal the surprising science and amazing manufacture behind these wicked inventions. A snowmobile is a vehicle designed for winter travel and recreation on snow. But just how were they first introduced?
A snowmobile is essentially what's considered an over-snow vehicle. It's not one that's ploughing through the snow, it's not one that's moving the snow aside, it is one that's designed to ride over snow such as it is. Snowmobiles were developed in Canada because it has a lot of snow, it has a lot of open ground, and has a lot of distance between communities. Joseph Bombardier developed in 1922 the design, which included twin tracks. Beforehand, there were wheels, there were skis, and it wasn't very effective.
The tracks on these newly invented snowmobiles could be easily modified. A good example would be detachable studs for better grip that wheels just simply couldn't compete with in wet and slippery conditions.
Joseph Bombardier improved snowmobiles over the next few years. He improved suspension, transmission, and braking because you need to be able to sometimes brake very quickly if something comes upon you that you couldn't see in advance.
Despite Bombardier's inventions and improvements, the first patent for a snowmobile was issued to Carl Eliasson for his motorized toboggan. Up until 1962, there were 13 patents granted to various snowmobile inventors. The second half of the 20th century saw the rise of recreational snowmobile use. The machines can now be modified to compete in longer, more drawn-out races, like Alaska's Iron Dog, which is the longest snow machine race in the world, at over 2,000 miles in length.
Snowmobiles, at least in the large form, were very useful. They could be used to transport lots of goods between communities, they could be used to move people faster, and obviously improve communication and improve healthcare, because in a snowy environment, there's not always a place to land a helicopter, but a snowmobile can get through distances much faster.
Brands such as Polaris ensure safe travel over snow, icy paths and roads. But just how are they made? Polaris, based in Minnesota, USA, produce snowmobiles for recreation and, of course, transportation in those long winter months.
Polaris has been making snowmobiles since the mid-50s. I think 1956 is the first year we built a snowmobile. The majority of the snowmobiles are sold in North America, Canada, US. We do sell some units to international, to Scandinavia, and also some to Russia.
The first step in the production of a Polaris snowmobile is the bending of aluminium sheets to form what is known as the tunnel. This tunnel will be the back portion of the snowmobile that the tracks ride in and is a vital part of the machine structure. All of this metal bending takes place in a specially built bending machine named the Bender, doing exactly what it says on the tin. Once the tunnel has been formed, it is loaded into a robot area that will see a series of robots passing the aluminium tunnels through a rivet process. These rivets are essentially extremely strong fastenings that can withstand all of the skids and slips that a snowmobile might face. The tunnel is then moved to the chassis assembly area. A robot first applies an adhesive to pre-programmed locations. With this completed, the operators then get to work assembling these glued components and fitting them to the tunnel in order to form the base chassis of our snowmobile. We can't forget about that all-important engine though. This is fitted next, using a hoist. That, along with the skills of the highly trained operators, means that the engine can be fitted in just 2 minutes, almost as speedy as a finished snowmobile. With the engine in place, the chassis over structure is then installed. This is what the steering components will be tied to, and at last our snowmobile is beginning to take shape. At this point, the completed chassis can be loaded onto the main assembly line. At the same time, the grippers and rear portion of the running boards are also installed. This is essentially where the rider's feet will sit when driving the snowmobile. A sway bar, otherwise known as an anti-roll bar, is then fitted to the machine. At this point, the cooling bottle that will hold engine coolant is also installed. A snowmobile isn't a snowmobile without its track. This is fitted next, again with great precision and speed. They can start and finish one of these machines in just 2 hours. Pretty impressive.
There's roughly around 100 operation sequences on the line. It's about 2 minutes per station. We build 180 units in an 8-hour day.
The next stage on the assembly line is the installation of the suspension structure, including the rear shock absorbers. These components need to withstand some serious bumps and jumps. From here, the handlebar steering post, as well as the steering assembly, is added to our snowmobile. The control arm is then attached to this suspension system. This is what parts such as the skis will be attached to later on.
Seasonality is an issue. One of the things I guess that plays into a big part of building snowmobiles is how much snow we get each year, and we have to, as a company, take a good guess at what we'll need to supply for the next year. One thing that Polaris does a real nice job on is we have a features and options program where the consumers can go in and order basically exactly everything they want on their snowmobile at a certain time of the year.
The snowmobile continues down the production line and really begins to make progress fast. The nose pan is fitted, along with the rear suspension, which is attached directly to the tracks. The all-important exhaust is then installed, as well as the clutch, the seat, and the hood. With the plastic outer shell of the snowmobile fitted, it is all but complete. After undergoing thorough testing, the snowmobile is ready for delivery, and more importantly, ready to tear up the snow. Snowmobiles, truly a wicked invention. Air conditioning may be a relatively modern invention, but the idea of climate controlling our homes is nothing new. With caves offering a consistent temperature all year round, it could be argued that they were humans' first air-conditioned dwellings. Harvesting ice from colder parts of the world and expensively transporting them to hotter areas seemed to be the only way to offer any relief from the oppressive heat of the summer months. But in 1842, a Florida physician named John Gorrie started to experiment with cooling the air for his patients with ice.
In the 1840s, Dr. John Gorrie invented a method to produce ice on site using an air compressor, which would compress the air, which would allow it to, and then once released, it would cool rapidly. That would produce ice on site, negating the need to get ice from North America and bring it all the way down to Florida. Still, it was a very labour-intensive process. It required horses, it required engines, and it wasn't very effective.
Unfortunately for Gorrie, his invention never caught on, and the ice trade continued to flourish, with ice even being transported as far as America to India. But he was approaching the problem of cooling air in the right way, by using pressurized gas. When using a deodorant spray, you might notice that it feels cool, and with prolonged use, the can starts to feel cold too. This is because of two reasons. The first is that the deodorant usually contains alcohol, which evaporates quickly, cooling your skin. The second is that the spray cools as it expands upon exiting the pressurized can. Whenever something under high pressure is released into lower pressure, it expands, absorbing heat energy as it does, which results in cooling. This vaporization occurs inside the can, and this explains why the can cools rapidly and why John Gorrie could create ice. While ice-making machines continued to be developed, the idea of cooling air seemed to die with Gorrie. It wouldn't be until 50 years after his death that another American inventor would accidentally stumble upon a workable air cooling solution. In 1902, Willis Carrier was trying to prevent his publishing company's magazine stock from getting damaged when he made his cool discovery.
The air in which they were stored was damp, and the problem was working out how to dehumidify the air. So what his invention was to pass the air in the warehouse over a series of long cool pipes. Passing the air over the pipes cooled the air, and as it chilled it, it took all the water out of the air. And now, what that wasn't intended to chill the air, it was intended to dry the air, but it had the effect of cooling it. So he solved the issue of the magazines going wrinkly when getting a bit damp, but also invented an air cooling system.
Carrier developed his large-scale air conditioning units further, and by the 1920s, they were cooling industry, theatres and government buildings across the United States. After the Second World War, smaller, more inexpensive air conditioning units were developed, which allowed homeowners to experience the cool effect of this new technology. So, what is the principle behind a working air conditioner?
If you expand a gas rapidly, it cools and it chills. So this is actually quite useful when it comes to air conditioning. If you have a gas that is compressed to a liquid, and then in a certain point you can release it so that it can become a gas, it can cool whatever it's in. If you're passing air over this system, you will cool the air because the air will naturally transfer the heat to the pipework and wherever it's needed, and then you can pump this warm gas outside of the building. The one thing that air conditioning does do, like with Willis Carrier's original design, is often they remove a lot of water from the air, so air-conditioned buildings can actually be quite dry.
In effect, air conditioners use the same technique to cool as your fridge. The secret to their efficiency is to use a refrigerant, which is a chemical or mixture of chemicals that can easily convert from a gas to a liquid and back again. Early air conditioning systems and fridges used toxic and flammable gases such as ammonia and propane, which could be dangerous if a leak occurred. Today, safer and non-reactive fluorocarbons are now used in the majority of systems. So, how does an air conditioner work? In addition to the refrigerant, the systems are generally comprised of a compressor, a condenser, and an evaporator. The refrigerant arrives at the compressor as a cool, low-pressure gas. The compressor squeezes the mixture and it leaves as a hot, high-pressured gas and flows into the condenser where it cools. When the refrigerant leaves the condenser, its temperature is much cooler and it has changed from a gas to a liquid under high pressure. The liquid goes into the evaporator through a very tiny narrow hole. On the other side, the liquid's pressure drops. When it does, it begins to evaporate into a gas. Warm air from inside the house is blown over the evaporator coils, and as the liquid changes to a gas and evaporates, it extracts heat from the air around it. This cools the surrounding air, and this is pumped back into the house. And the refrigerant gas cools and returns to the compressor to begin another cycle.
One of the benefits of air conditioning is hospitals. If you're a patient and you're ill, the last thing you need to do is to try to fight to keep yourself warm or fight to keep yourself cold if you're ill. That puts an excessive strain on the body. That's one of the major benefits, to my mind, of air conditioning. On the other hand, the other benefit is comfort. Simply put, if you're in a hot environment and you want to remain cool, air conditioning can allow you to do that, and if you have good insulation, it can actually be a very efficient method of keeping a house cool and comfortable so that we don't have to expend all our energy on keeping the body temperature as we need it. So, for example, in Saudi Arabia, where it's, say, 50 degrees Celsius outside typically, you can walk into an ice-cold mall, have an ice cream, and even go ice skating.
Keeping us cool, even in a blazing hot desert, makes air conditioning truly a wicked invention. Can we make an aircon unit with old computer parts? We're going to need 2 UPVC pipes, a styrofoam box, an old computer fan, and a craft knife. To begin, we cut 2 holes in the styrofoam box's lid for the 2 UPVC pipes and fix them in place. We then cut another hole in the back of the box and secure the old computer fan. We fill the box with ice, stick on the lid, and we are ready to go. We measured the ambient air in the laboratory. A rather warm 28 degrees Celsius. Let's cool things down. We switch on the fan, and with the air flowing out of our UPVC pipe ends, let's see if our DIY aircon unit is working. Wow, a chilly 15 degrees Celsius is now blowing out of our little unit. Much more comfortable. The computer fan directs air from the room into the unit, over the ice and out of the UPVC pipes. We would assume that the air cools as the coolness of the ice radiates onto the warm air that passes over it, but this is not the case. In fact, the excited, warm air flowing over the ice bumps into the molecules of the ice and transfers energy to them. This causes the air to lose heat and be cooler. So the air transfers heat to the ice instead of the ice transferring cold to the air. Can we make an aircon unit with old computer parts? Yes, we can. Wicked challenge smashed. The immersion suit, which is also known as an anti-exposure suit, is a special type of waterproof dry overall that protects the wearer from hypothermia in cold water. But just how were they introduced?
They are basically there to provide protection from the elements to people working within maybe the sea or rivers. Wherever there's a body of water, there's always been that fear that you're going to fall in it. The first immersion suits really came about in the early 1900s in America, and a guy called Clark S. Merriman created a very simple kind of suit designed for anybody working around the sea in boats.
The first suit was made from rubber sheeting. It was essentially a pair of rubber trousers and a tight shirt with a steel waistband holding the two together. Air pockets allowed this wicked invention to be inflated by mouth, a feature still used in a lot of dry suits today. These early immersion suits played a big part in getting those in danger to safety without exposure. This is mainly because most rescue services and emergency radio transmitters were yet to be invented.
If that wasn't enough, Merriman even attached a small sail to the chest, so you could be floating there with a small sail kind of blowing you along. Ingenious invention, but it did inspire the American Life-Saving Company in 1930 to create their kind of all-in-one immersion suit. And this is really the first commercially advertised and sold suit.
Today, these survival suits are normally made out of bright fluorescent neoprene for high visibility on the open sea. The neoprene material used is a synthetic rubber closed-cell foam containing tiny air bubbles, making the suit sufficiently buoyant to also be a personal flotation device.
As the human race has increased its relationship with the sea, you think now we have oil platforms, we have increased shipping, cargo haulage. Companies have sprung up to create more and more life-saving equipment, but essentially the initial design hasn't changed from its original founding by Merriman back in the late 19th century.
These life-saving suits really are wicked inventions, but just how are they made today? Viking life-saving equipment produce highly flexible, combined work and anti-exposure suits that allow users to stay safe and mobile in even the harshest of maritime conditions.
Viking was established in 1960 producing primarily life rafts, but since the early 80s we've also been producing protective equipment, meaning immersion suits, life jackets and fire suits. Currently we're about 2,000 staff worldwide with offices pretty much all over the globe.
The production of one of these anti-exposure suits starts with design. This will begin with a brainstorming process that will then go on to a mood board. Designers and engineers will look at three main points when designing their immersion suit. First and foremost is safety, next is functionality, comfort and fit, and then finally the aesthetics of the suit. Once the mood board has been discussed, the designers will then construct the suit digitally, using computer-aided design or CAD software. This allows them to look at every inch of the suit in depth and make alterations where needed, without having to make a single stitch. With the design complete, the information from the design software is inputted into a CNC machine that will then cut out all of the relevant patterns and components needed to form the finished anti-exposure suit.
Having a full accuracy in the cutting ensures a consistency and a quality in the overall product. So getting started right ensures that you get the right flow through the entire production.
The process is set up in such a way that it keeps fabric wasted to an absolute minimum. Working a bit like a reverse jigsaw puzzle, the machine will choose exactly where to cut out each separate component to maximise the material used. The cutting table itself is also quite important. This table contains tiny holes. Under these holes is a vacuum, sucking down on the fabric so that it stays in place and can't move when cutting is underway. Imagine an air hockey table that pulls instead of pushing out air, and that's pretty much what this vacuum table is. With all the components cut to shape, it's time to begin the sewing process. Here the anti-exposure suits all come together as one, with many sewers all working away simultaneously to bring it together. Although they may not look it, these sewing machines are a bit different to the everyday sewing machine you might find at home. They can stitch at exceptional speeds with great precision, making sure that every seam is exactly right. That's the sewing finished. It's time now to work on the seams of the suits to ensure that it is completely watertight. A combination of heat, glue and pressure ensure that the seams are very firmly sealed shut. These highly trained operators will constantly check the seams as they work, as accuracy here is vital to the safety of the anti-exposure suit's end user. These special seam sealing machines are highly accurate, and the operators know exactly the right speed to operate the machine so that it seals perfectly.
One could argue the more features you have on the suit, the more sewing and the more seam sealing, but it's very, very key that you master the seam sealing to make sure that you get a high quality product and a durable product down the road.
The customizable elements such as boots and collars are then mounted to the anti-exposure suit. This is all glued and sealed together by hand, with just as much care and attention as with every other element of the suit. Now that we have everything in place and sealed, this anti-exposure suit needs testing. Every single suit is tested before dispatch. The suits must be turned inside out and then filled with water so that any leaks can be spotted. An operator will check every inch of the suit, front to back, to ensure its safety.
Every single suit that comes through production or every single suit that comes through our service network will be serviced in the exact same way, ensuring 100% compliance and 100% integrity of the product before it meets the end user in a critical situation.
These tested suits can then be hung and placed into this huge dryer for 2 hours. As well as this, the bladder of the suit that works much like a life jacket, giving buoyancy to its wearer, is also tested. Here the bladders are inflated to 400 millibars of pressure for 1 hour. After this hour, another measurement is taken to ensure that the pressure is still the same. This is then repeated with a slightly lower pressure. If both tests are passed, they're good to go. Once dry, the suit is packed up and sent around the world, ready to be called into action when needed, and save lives in the process.
This type of product is being used pretty much from Navy, across oil and gas industries, to the fast rescue boat operators on a cruise line, to the local fishermen. So in that regards, we try to take a lot of input from different industries to make sure we find a product that would fit the end users in all these different segments.
Anti-exposure suits. Now they really are a wicked invention. So, there you have it. A dash through the hidden history, super science, and amazing manufacture of products that you use every day, but have never realised their amazing backgrounds. Snowmobiles, air conditioning, and the immersion suit. All wicked inventions.